have learned how to utilize our Navier-Stokes to analyze some flow. Okay. We have briefly go through how to analyze the flow between two stationary plates, right? And then what happened when the one of this plate is moving or both plate is moving. Basically, if you look at how we analyze it, is that the general solution is the same. The only difference is when you implement the boundary condition. Different boundary condition will give you a different set of equation at the beginning. Oh, sorry, at the end. But the generic solution will be the same. And also, I have shown you two different driving force that can drive the flow. That is gravity and pressure gradient. Okay, and I have shown you that in some cases both may present, right? In the tutorial class, question number 2, question part B. If you come to my tutorial, I know most of you skip it. It's up to you if you do not want it. It's totally and entirely up to you. But don't cry during the exam. Okay, I will not pay any whatsoever. Okay, so if you do not come to my tutorial and you complain to me, oh, this one is not your class. Yeah, that's it. Okay. So in the tutorial, I have shown you how we can utilize both driving force to drive the flow, right? Both dp dx and gravity. So we have gone through it. In my tutorial number 5 and in the lecture note, I have also given you the example of a tube flow, but that one is for enrichment, for self-study. Okay, so you can, if you are interested to look at it, you can do it on your own. I know you have a smart brain, you can do it on your own. Okay, but what I can say is this tube flow will not be in the exam because I'm not explaining it on my class and tutorial. But the tutorial got the answer, and the lecture note also got the answer. So if you want to try on your own for your own good, you can do that. Okay. Now we will move to the next part. If you remember last time I told you we have several topics to be covered. One is the introduction of the Navier-Stokes, because that one is the basic that we will use along again and again, right? The second one is the external flow. This one is related to aerodynamics. Okay, aerodynamics. This one is one topic that usually attract the attention of my student, my previous student. They love it because this is where you can design your car, this is where you can design your house, this is where you can design your airplane. Okay, it is not offered in UTP, but when I take my PhD in NUS, there is in Singapore, there is one course called building aerodynamics. You know, when you have a tall building like the one we have in the LCC, or even worse if you go to Dubai. In Dubai you have Burj Khalifa, in Mecca you have Clock Tower. Now they build another high-rise building which will stand above 1 kilometers, 1,200 meters or something, if that thing is not broken down before the Nila. Right, so it will be very tall, and you know, in those tall buildings, the shear acting on the surface can drive the tip of the Burj Khalifa up to 4 meters. So we'll do that, and from the tip to the deflection can be as far as 4 meters. Imagine that. Of course, you will not feel it because it will move not like your trees where you do that, it will just move slowly. But When there is a strong wind, it can deflect up to 4 meters. Right? But of course, the top one is not occupied. You know, the top one is only a tower for communication. There's nothing there. The highest habitant space is only 600 something. And that 600, if you have fire, is enough for you to kill yourself. Right? Don't believe Tom Cruise. He can drive the car from this building to that building at that high. For sure, Tom Cruise still alive for you. Bye-bye. So this is where we know how to do that. Okay. So in the previous lecture, we have to know how to formulate your conservation of mass and momentum, and then develop the Navier-Stokes equation, and then you implement it for certain flow, right? Flow between parallel plates, and then flow between parallel plate where the top or the bottom plate is moving. I haven't tell you the name of that kind of flow is flow. Okay, if you know how to speak French, then you know how to call it. But for me, I do not know, so I never tell my student how to properly pronounce this. If some of you knows French, you can tell me how to do that. Okay, flow down inclined plate and flow down a vertical plate. That too, I have briefly shown you that the driving force will be the gravity, right? So everything else will be the same. The only difference is the gravity, and different in boundary condition. If you have wall, then your U will be equal to the U of the wall. It can be 0, it can be big U. When there is no wall, you will have a free surface. When you have a free surface, your du dy will be equal to 0. Because the shear exerted by the air is very small. Okay, so that's what we have learned. So here, okay, I would like you to remember what is the difference between viscous flow and inviscid flow. The pressure. When you derive your Bernoulli equation, do you take into account the viscosity effect? Bernoulli. Yes. Bernoulli equation. No. So when there is no viscous effect, your flow will have the same velocity across the pipe. So when you have a pipe, imagine this one is your. Why the whiteboard now getting smaller and smaller and smaller? Last time I remember we have big one, right? Now it's following my body, it's getting smaller and smaller. Okay, so if you have inviscid, the flow will look like this. Okay, the wall does not have any effect, so the flow is just going there. When you have a viscous flow, then this is what you will have. See the difference? So this one is in, you see it? This one is called. Yeah? Now, why do we care about inviscid? This inviscid flow is, okay, easy to solve. If you have steady inviscid flow, you will end up having Bernoulli equation. Of course, you are happy with Bernoulli equation rather than Navier-Stokes equation. Any one of you love Navier-Stokes more than Bernoulli equation? Let me know. Then I will make a special class for you. Right? It can be solved easily using Euler equation. Euler equation is this, but most of the time your flow is steady state, so it's gone. And your flow is incompressible. So at the end of the day, you're just having this one become V square, rho V square. I told you last time, right? When you have V, dV, x is nothing but your, actually this one is, you get your dv squared dv dx. So at the end of the day, you just have dv squared. These two, same. That's why in your Bernoulli equation, you get this. Okay, so one come from here. Okay. This, and that will give you Bernoulli equation. Okay? If you don't trust me, derive it on your own. Okay? And I hope you are not trusting me, so you will derive on your own. So, yeah, why implicit? Because it is easy to solve. That's it. Is it real? No. There is no such thing of implicit flow. But it is very good approach. Right? No fluid resistance. Then, how about viscous flow? Viscous flow is the real flow. Okay, this is flow that we are facing every day. This is the real flow. But the problem is, it is represented by the much more complex Navier-Stokes equation, which most of you do not like to have it, unfortunately, but it is there, right? And the flow will look like this, exactly what I write, right? This is implicit, that is viscous flow. In real life, that's what happens. Even when you are having air, where the friction is very small, still, this thing will happen. Okay, just the thickness of this will be different. And this will give you the good accuracy of your analytical of that flow. You know, it will closely represent your flow. But the problem is, it's complex. So, you want to get the simplicity of implicit flow, but having the accuracy of that the viscous flow.